Okay, so now we're going to look at a banked curve problem, and this is one of the standard problems in physics that every student loves. It drove me crazy as an undergrad, but I'm going to show you how to think about this so that you don't make the same mistakes that I made. Okay, so first of all, what is a banked curve, and why do we have roads that are banked? All right, so a banked curve just means that the road, instead of the road being completely flat as you're going around a curve, the road is kind of tilted so that there's a bank. Okay, so if we're to draw this banked curve, okay, so I'm kind of drawing an exaggerated version of it, and this represents the cross section of the road. So in a sense, we're looking at this as if your car is like your car is driving into the page, so that you're looking at the back of the car driving away from you. So this is, if you're going around a curve, the road is tilted like this rather than just being flat. And there's a reason for that. Okay, so if we draw the force diagram for this banked curve, okay, so let's just look at the forces here. So we've got the weight down, we've got the normal force up like that. And let's just suppose for the moment that there's no friction on the road. Let's say it's completely icy, there's no friction. So then if the center of the curve, let's imagine that the car is going in a circle so that the circle is kind of in and out of the page, but the center of that curve is somewhere like this. So if you imagine the car making a circular path as it's going around this track, just pretend it's like some kind of a racing track, perhaps, where it's banked. All right. Well, in this case, remember what we're trying to do is we're looking at our RTZ axes, okay? And we're looking at the R axis as being the one that's the radial axis, and that's the one that's going to involve the circular motion. So in this case, you can see that the R axis is going to be along like this, yes, toward the radius, along the radial direction. Okay. Now, what I want to make sure that you understand is that when this car is driving on this banked curve, it is not sliding up the ramp. It is not sliding down the ramp. There is no sliding happening up or down the ramp. But the car, the only motion of the car is going in this circular path that is into the page at this point in the drawing. So in order for us to maintain a curved path, we have to have a centripetal force. Well, in this case, look what we have. We have part of this normal. We have this x component of the normal force that's acting along the r axis, and it's that normal force in the x direction that will serve as our centripetal force. But what if we didn't have the banked curve? What if we just had it flat like this? And we're going around and we drew our force diagram like this, okay? Now, in this case, if we're trying to go around in a curved path, we have to have some force pointing in toward the center of the curve this way in order to maintain that curve. Many times that would be served by a friction force. So if you have a flat surface and you're trying to maintain a curve in that path, you're going to need some friction or maybe a rope and have some tension. Something's got to provide that force. But what if there's no friction? What if you have no friction? What if it's icy? Well, now you're out of luck. There's no way you can maintain this curve unless you go back to the banked curve and you see that the normal force, part of that normal force component, is acting in the centripetal direction. So that is why we have banked curves. It's so that we can maintain safe speeds on the road even if there's no friction, okay? And highways are designed so that they have curves that are banked at certain angles so that the normal force will provide the necessary amount of centripetal force for that curve, for that whatever the radius is, and the posted speed limit. And you might say, well, what about, does it matter, you have light cars and heavy trucks. Does that make a difference? No, it does not, because you'll see that the mass cancels out and is irrelevant, which is really convenient for designing highways. Okay, so let's get back to this problem. And just for clarity, I'm gonna draw this a little bit better here. All right. Okay, so the other thing that I sort of alluded to but didn't actually fully explain is that we want to set up our axes. Okay, so this is the R axis. The Z axis is going to be the vertical. And in this case, the tangential axis is along the direction of motion or into and out of the page. And in this example, there is no force that's tangential, so we can kind of ignore it for this problem. There'll be plenty of other things to deal with. All right, so we have our force diagram. And we are, let's make another assumption. We do have friction. So let's put friction, in there too. Okay. Now, when you're doing the bank curve problems, one of the things you need to do is to check whether you're looking for a maximum speed or a minimum speed. So let's suppose we have no friction on this surface whatsoever. If we try to go too fast, ask yourself what will happen if we go too fast and there's no friction. Which way will the car want to slide? The car will want to try to slide up the ramp if you go too fast. So you would need a force pushing you down the ramp like this, and this is our friction force. Okay? Now, what if it asked you what is the minimum speed? What if it was so icy that you could barely go and you're going so slowly that you actually start sliding down the ramp like toward the median of the road, which actually did happen to me one time years ago. So I can tell you there is a minimum speed you have to maintain so that you don't crash into the median like the other cars that are doing it. So anyway, so if our tendency of the car is to slide up the ramp, we need friction to act down the ramp. Okay, so now ask yourself, what kind of friction is acting? Is this static friction? Is it kinetic friction? And why? In this case, it's going to be static friction because we don't want the car to slide sideways whatsoever. We're not trying to race. We're not doing any drifting here. So we don't want our tires to slide sideways whatsoever. So the tires must be completely firmly planted in the side-to-side direction. All right. Now we have our forces drawn. The next step is to draw the components. So let's get the components of our forces. Okay, so the normal force is going to have a normal and Z component. The normal force is going to have a component in the R direction. Next, we have friction. Okay, so this friction force now has to be broken up into the axes. So we've got some of our static friction that's acting this way. So I'm going to call that friction R. And some of our friction is acting into the incline. It's sort of digging down into the curve, down into the pavement. Okay, not passing through it, but just, digging down in. Okay, so we have our friction in the Z direction. Okay, now that we have our force diagram, we are ready to start applying Newton's second law all over the place. Okay, let's apply Newton's second law to the r direction. Okay, so some of the forces in the r direction. Remember, this is the centripetal axis, so we're going to say that's equal to mv squared over r. Also, remember the sign convention for doing the centripetal axis, doing the radial axis. Remember how we determine positive or negative forces. The way that we do that is any forces that are pointing inward are going to be positive. If the forces are pointing out of the curve, out toward the outside of the curve, then they're going to be negative. In this case, both n sub r and f sub r are pointing toward the center of the curve. Both of them will be positive in this case. Okay, so we've got friction r plus normal r. Okay, and that's going to equal mv squared over r. Okay, notice that this v is the v that we are trying to solve for, by the way. Okay, well, let's get some angles. Let's see, we know our theta, our 15-degree angle is here. And that angle is going to be here as well. And you might recall from our previous discussions of force diagrams on ramps that we used to have, we used to say that our y-axis, no, you can't see that very well. Let me make a different color here. We used to say that our y-axis was this axis like this, yes? And we said that the angle of the ramp was in here. Well, that is just going to be related to the angle at the top up here because of them being, I guess, alternate interior angles. I think that's the name of them. Okay, so let's go back. All right. So that means that we can also put our angle, it's also going to be in here as well. And the way that we can see that is because we have this line and this line cut by this transversal so that this angle and this angle will be equal to each other. All right. Okay, so the friction in the r direction, that's going to be friction times the cosine of the angle. And then we have the normal r, that's going to be the normal force times the sine of the angle. Because that normal force in the r direction, that is also up here, which is the opposite side in that triangle. So it's going to be the sine. Okay, then over here we've got still our mv squared over r. All right, well, we don't know what the value of the normal force is. We can go ahead and go to the other axis for that. Oh, you know what we can do? Let's substitute for friction here. Okay, so that's going to be mu times n. That's good. That pops out another normal force for us to be aware of in our expression. Okay. So let's go to the y direction now for the normal force. I'm sorry, not the y direction, the z direction now. Changing things up. Okay. So the sum of the forces in the z direction equals ma in the z direction. Remember, this is one of our linear axes. This is not our centripetal axis like the r axis was. Okay, and because we have no motion along the plane whatsoever, that also means we don't have any motion. We have constant velocity of 0 acting along the z-axis as well. We have no, the car is not lifting up off of the incline. It's not sinking down into the incline. So this is going to be a 0 acceleration on the right side. Okay, so we've got upwards, we have n sub z. Downward, we have f sub z, and we also have the weight. Okay, so let's flesh this out a little. So the n sub z is going to be n times the cosine of theta. Okay, let's go to the friction force. Friction in the z direction is going to be friction times the sine of the angle. And I'm going to put the weight on the right side of the equation and just make that mg right now. Okay, so let's do another. Oh, we have a system of equations here. Yay, fun. Okay, so let's get this substituted. All right. Now let's look at what we have. We're trying to solve for v. We also have n. We have normal force as our unknown. So I'm going to go to the second equation down here, and I'm going to solve this. I'm going to solve this for the normal force, and then maybe plug it in up there. Okay. So let's factor out the normal force. Okay. And that means we're going to have mg all over cosine minus mu sine theta. Okay, so that's our normal force. And I'm going to go ahead and pop that into our other equation. Let's just move that over. Okay. So now I'm going to go up here. And you know what? I'm going to solve this for v first, and I'm going to factor out the n so that I can just pop in one value of the normal force. That's my plan. Okay, so let's see how that works. So first I'm going to, let me factor out the normal force. Okay, now I'm going to solve for v. All right, so that's going to be r times all of this stuff. Okay, all over m, and then square root it. Okay. That'll make it a little bit easier. Now I'm just going to put in the normal force one time and not have to plug it in twice. Okay, so let's do that. So I've got r. Now I'm going to put in the normal force, and that's going to be mg over cosine theta minus mu sine theta. Okay, that's the normal force. And I still have the quantity up here, which you would hope that it might actually be similar enough that it could cancel or combine, but no, sorry, no luck. No worries, we'll still make it work. Okay, so now we've got the m's canceling. And let's clean this up a little. Yeah, so we can make this rg mu cosine theta plus sine theta all over cosine theta minus mu sine theta. Okay, so let's see. All we need is our radius, which I believe is given to us. We need the mu, and we need the angle. So let's go back and look at some of the givens, and let's write them down. Okay, mu and the angle. All right, let's wheel it back up. A radius of 70 meters banked at 15 degrees, and we are looking at a concrete highway and rubber tires. So we're going to go over here to the chart and we're going to look for the correct the correct coefficient of friction, which is the static coefficient in this case. And we want rubber on dry concrete. So this is the one that we want to look at. So the coefficient of static friction for this set of surfaces is 1, which is, that's as high as it gets, and that's pretty good. Okay, let's go fill in our values. So this was 70 meters, and mu is equal to 1, and theta is 15 degrees. All right. So now that we have all that, let's go and plug and chug. Okay, so cosine 15 degrees plus sine of 15 degrees. Okay. All over cosine 15 degrees minus mu times sine of 15 degrees. All right. So let's see if that turns out. And that should give us the answer. Let's see what we get. I'm just working this out on my calculator. Maybe I should have done it ahead of time, but we're just going with it. Okay. Okay, and then just square root that. Okay, so what I got was to 2 sig figs, it rounds to 34 meters per second. Okay. This comes out to about, I think if you Google that, I think it comes out to roughly, I think it's about 70 miles per hour, roughly. Don't quote me on that. You can look that up. But this is the answer in meters per second. So let's go back and look at what we did here in this problem. Okay, so there were a couple things going on. The banked curve means that we're going to set up our RTZ axes so that the R-axis is along the curved for the circular motion. And we were careful to determine what direction the friction force acted. In this case, it's down the plane. And we drew our force diagram. We put our axes on there and split up our components, applied Newton's second law in 2 of our axes, got a system of equations, and solved for the unknown. And that's pretty much the same method that we've been using for all of these problems in this chapter.